In the previous video, using the mass conservation law, the water level control tank system under study was expressed in the simple first-order differential equation. The differential equation states that the volumetric flow rate in minus the volumetric flow rate out equals to the rate of change of the water level height. This means if the input and the output volumetric flow rates are equal, no change will occur to the water level height. Also, from this equation, if you set the volumetric flow rate out to 0, then the process is a pure integrator. That is, nothing counteracts the increase in the water volume. So you can simply set the flow rate to reach the desired height in a fixed time interval. However, if you assume a fixed leakage or an output volumetric flow rate exists, then the output volume flow rate will depend or will increase as the liquid height h increases. If you recall, the water level control steady state response was 0.667. This means the discrepancy from the input is 0.33. In general, assuming a tank filling during a rainfall, if you assume the flow rate is stepped up from 0 to an input of 1 meter cube per minute via a voltage controlled valve, then we do expect that the height will reach the 1 meter in 1 minute if the area is 1 meter squared. However, it will only reach the 0.667 instead. The reason is because the output volume flow rate increases when the liquid height h increases, but then the increased level results in a larger outflow, and we eventually reach at time equal to infinity a balance point where the volumetric flow rate out equals to the volumetric flow in, hence h is no longer increasing. To find out how to minimize or eliminate the steady state error, let us draw the water level control tank system block diagram to investigate how the controller, which was previously assumed as one, play its role. You will later learn that the proportional control can be used to alter the rise time and the settling time of a first order system. Also, by increasing the proportional gain, the steady state error can be reduced. However, to achieve a zero steady state error, the gain would have to approach infinity, which is impractical. Therefore, for a first order system, a proportional controller cannot be used to eliminate the step response steady state error. On the other hand, the integral component of your controller helps reducing the steady state error, and in some cases, depending on both the system type and the type of the reference signal, the steady state error can be eliminated. If you recall from previous session, we have calculated the steady state response of 0.667 by first finding the closed loop transfer functions for both the S domain and the Z domain. Then we have applied the final value theorem. In order to calculate the steady state error, you could either find the error relation and then apply the final value theorem, or alternatively, you could use the error constant method. The error constant method involves the calculation of the position, velocity, and acceleration constant errors. However, you have to note that these constants are defined with respect to the forward path transfer function with a unity feedback loop. The objective here is to establish a relation between the steady state error and the system type for one of the basic system configurations, i.e. systems with unity feedback. There are other studies for systems with non-unity feedback, but will not be tackled in this analysis. It will be shown clearly how the steady state error depends on the number of poles at the origin, and this is what is known as the system type. To identify the system type in the continuous S domain, first you need to identify the transfer function and the forward path. Then find the number of poles in this transfer function at the origin. This is done in a similar way in the Z domain. However, the only difference is you need to find the number of poles at the unity circle, i.e. Z equals to 1. If we assume the controller again as 1, then the forward path transfer function in the Z domain is the combination of the zero order hold and the plant transfer function, which was obtained in the previous video. And since no poles at the unity circle, then the type is 0. To find the relation between the system type and the steady-state error, first we apply the final value theorem. Once we find the error relation between the input and the output, we can substitute back this relation in the final value theorem to obtain the general form as shown here. It's clear that the steady-state error depends on the input and the forward path transfer function. If we assume the input is a unit step or a step of magnitude r, where r is equal to 1, then the s's cancels and the limit as s tends to go to 0 for the forward transfer function can be denoted as kp. Now kp is the position error constant, and this is because the input is a step. Since our forward transfer function is just the plant transfer function, if we substitute s equals to 0, then kp equals to 2. And the steady-state error in this case is 1 over 3, which is 0.333 as obtained before. But how the system type affect the steady-state error? Suppose that we have the following forward transfer function with an added s in the denominator, i.e. the system type now equals to 1. If we apply the steady-state error relation again, we end up with a steady-state error of 0. We can conclude with the step inputs. The steady-state error is constant for a system type 0, and it is 0 for type 1 or higher. One way of increasing the system type is by simply adding an integrator in your controller, and this is what was discussed at the beginning of this video. We cannot emphasize often enough that for these results to be valid, the closed loop system must be stable. The steady-state error of first-order systems with a step input with magnitude r can be shown graphically as follows. Please remember that the transient response is determined mainly by your controller and the characteristic equation. A similar analysis is applied in the Z domain. We can start off by writing the final value theorem. In order to find the error in the Z domain, first we could find the E star in the S domain, and then we can substitute the Z equal to exponential of st. Please refer to previous videos for more information. It's clear that we have arrived at a similar relation to that obtained in the S-domain. If we assume the input is a step with a magnitude r, applying this in the relation of the final value theorem, cancelling the z minus 1 in the numerator and denominator, and applying the limit for z equals to 1 for the forward path transfer function, we obtain the steady state error of 0.33 as well. Also, if we increase the system type, the steady state error will be 0 in this case. We can also show this graphically in a similar fashion to that done in the S-domain. So for system type 0 with an input of a step with the magnitude r, then the steady state error is constant. When the system type is increased to 1 or higher, we expect the steady state error to be 0.